Welcome to the class of complementary slackness conditions of linear programming problem. Complementary slackness conditions are very important tools in understanding the relation between the primal problem and the dual problem. These conditions are also useful in obtaining the optimal solutions of one problem, say primal, from the another problem, which is the dual problem method. In this lecture, we will study the complementary slackness theorem without proof. We will also implement this theorem on the numerical examples on the by using simplex table as well as by using the graphical method. So let us state the complementary slackness theorem. Let x bar be a feasible solution of the primal problem, say P, which is maximizing C transpose X subject to Ax equal to B, Ax less than or equal to B. Let us consider the problem in canonical form. X greater than or equal to 0, and let W bar be a feasible solution of the dual, which is say minimize P transpose W subject to A transpose W greater than or equal to C W non-negative. Then X bar W bar are optimal solutions of the respective problems if and only if x bar and w bar satisfies the following conditions, that is w bar transpose into ax minus b is 0 and x bar transpose into c minus a transpose w bar is 0. So these two conditions are basically called complementary slackness conditions, also abbreviated as CS conditions. So this condition says that at the optimal primal dual pair x bar w bar, this product is 0. Now what is the meaning of this product? So let us look at this product first. You see from here that if I look at ax bar ax minus ax minus b, ax less than or equal to b, so this implies ax plus identity times some s is equal to b, where identity time s means that we are adding the vector of slack variables which make it an equality problem. So that means ax minus b is nothing but what is identity times the slack variables. So if this product ax minus b is 0, this simply means that the slack variables are 0. So that means if I look here at this product, it says that at the optimal table or at the optimal solution, if w bar is an optimal solution of the dual problem, it gives the information about what slack variables in the primal problem are 0. Similarly, we look from this condition that if x bar is an optimal solution of the primal problem, it gives us the information about which of the slack or surplus variables in the dual variable are 0 and vice versa. Let us understand it in a more detailed form. So we rewrite these conditions in the following form, like In the optimal solution of primal, if in the optimal solution of primal, if the ith variable is strictly positive, then the ith dual then the ith dual constraint is satisfied as an equality constraint, which means that the ith slack or surplus variable in the dual problem is 0, which is same as we discussed here. So if w bar, or say if because x bar is the optimal solution of the primal problem, so if x bar is non-zero, then this component has to be 0. But what is this component? This component is nothing but the slack or the surplus variable. Okay, so this is what this condition says. Now let us understand the second form of this condition. So in the optimal solution of primal, if ith slack or surplus variable is strictly positive, then the ith dual variable is 0. That is, so we can understand from here, like if this is 0, if this is strictly positive, then this has to be 0. Or if this component is strictly positive, then one of the variable here, the one of the component here is will assume the 0 variable. So one of the component here will assume 0 value. So essentially there is a relationship between the primal variables and with the slack or surplus variables of the dual problem. So if the primal variables are positive, then the corresponding slack or surplus variables are assuming 0 values. Now let us understand these concepts by means of an example. So consider an example: maximize 5x1 plus 4x2 subject to 6x1 plus 4x2 less than or equal to 24, x1 plus 2x2 less than or equal to 6, minus x1 plus x2 less than or equal to 1, x2 less than or equal to 2, x1 x2 greater than or equal to 0. So since this is a two variable problem, we can always solve this problem by using graphical method. Now suppose we are able to solve this problem, and the optimal solution of this problem is x1 equal to 3, x2 equal to 3 by 2 with z is equal to 21. So 3 comma 3 by 2 is the pair which is the optimal solution of this problem. Now in order to implement the complementary slackness conditions, we must write the dual because we want to find the optimal solution of the dual problem. So what we need to do in order to find the optimal solution of the dual problem, we know that both these conditions need to be satisfied. That is, we need to know which of the variables are positive, and also from the second condition we must know which of the slack or surplus variables are positive. But from this optimal solution we can understand that we have the information about only x1 x2. But if we look here at this problem here, that this constraint, this essentially means that it is 6x1 plus 4x2 plus s1 is equal to 24. S1 is my slack variable. So in total this problem has four constraints, four more variables which are like x1 plus 2x2 plus s2 is 6 and so on. So that means the complete set of variables of this problem are x1, x2, s1, s2, s3, s4, where s1, s2, s3, s4 are the slack variables in the first, second, third and fourth constraint respectively. But we have the information of only first two variables 3 and 3 by 2. In order to implement our complementary slackness conditions, we must know the value of these variables. If we put the value of 3 and 3 by 2 here in the first constraint, if I put my value here, see from this constraint, you see 6 into 3 plus 4 into 3 by 2 is 24. So that means the slack variable is already 0 here. This constraint is satisfied as an equality constraint. That's what we were talking about. So this variable has value 0. Similarly, second constraint also is satisfied as an equality constraint. So the value of second constraint is also 0. The value of third constraint comes out to be, third variable comes out to be 5 by 2 and 1 by 2. So this is the complete optimal solution of the problem, right? Of course, we can write here like 0, 0 s1 plus 0 s2 plus 0 s3 plus 0 s4 if we are writing the problem in standard form. Okay, but the more important point is that we must understand what is the optimal solution of the dual problem. So this is 5 by 2. Okay, so let us write the dual problem here. So what is my dual problem here? So my dual problem is minimize 24 by 1 plus 6 by 2 plus by 3 plus 2 by 4 subject to the constraints 6 by 1 plus by 2 minus by 3 greater than or equal to 5, 4 by 1 plus 2 by 2 plus by 3 plus by 4 greater than or equal to 4, by 1 by 2 greater than or equal to by 1 by 2 by 3 by 4 greater than or equal to 0. Okay, now let us see how the complementary slackness theorem works here. Here y1, y2, y3, y4 are my dual variables corresponding to each of the constraint of the primal problem. Now the complementary slackness theorem says if some of the variable, see if x1 is positive in the optimal solution of the dual problem, this tells me that the first slack or surplus variable in the dual variable is 0. So first write how many dual variables we are having. So if we put this problem in the standard form, we need to put one we need to put surplus variable here and surplus variable here. So in total, if this problem has to be put in standard form, so we have 6y1 plus y2 minus y3 minus S1 bar, I'm using bar for the slack surplus variables for the dual problem, is equal to 5. And the second constraint when put in standard form gives 4y1 plus 2y2 plus y3 plus y4 minus S2 bar is equal to 4. So we have these two. Okay. Now let us apply the CS condition. So it says, so we have in total how many variables? We have y1, y2, y3, y4, s1 bar, s2 bar. These are the 6 dual variables. So what information we are dragging from this? Now we see that x1 is positive. This simply gives us the information that my s1 is 0. Okay, so since x1 is positive, that means my first dual variable is taking 0 value, because primal variables are connected with the slack or surplus of the dual variables. Or in other words, we can also understand, because if s1 is 0, that means first dual constraint is satisfied as equality constraint, because here s1 is 0, so this is a equality constraint, right? So that's what my complementary slackness condition here told, that if in the optimal solution of the primal, if ith variable is strictly positive, then the ith dual constraint is satisfied as the equality constraint. So my first variable is strictly positive, that means my first dual constraint is assumed satisfied as equality constraint. Now similarly we see that here from this information that x2 is also positive because its value is 3 by 2. So that means my s2 should also take my 0 value. These two variables are not giving any information. Further, s3 and s4. See in this basic solution there are 4 positive variables, and it has to be. Why? Because in the primal there are 4 constraints. You see, where is the primal problem? So this is the primal problem, right? So we have 4 constraints. So in the basis we have 4 variables, and we have identified these 4 variables in the basis. Which one? X1, X2, S1, sorry, S3 and S4. So first two variables of the basis give us the information that these two surplus variables of the dual problem are 0. Now what does these variables are giving me the information, because they are also in the basis. Now my third slack variable is positive. This is giving me the information that third dual variable has to be 0. So that means my y3 also is 0. Similarly, fourth slack variable is positive, means my fourth dual variable also has to be 0. So substituting all these values in this set of constraints, what we get? We get 6y1 plus y2 is equal to 5, 4y1 plus 2y2 is equal to 4. On solving these two, we get y1 is equal to 3 by 4, 3 by 4, y2 is equal to 1 by 2. And if we put the value of y1, y2 in the objective function, you see what we get. We put the value here in this objective function. So what we get? We get, so z value comes out to be 24 into 3 by 4 plus 6 into 1 by 2 plus 0, 0, 0, because all other things are 0 here, right? So what this value we are getting? So this is 6, 18, 18 plus 3 is 21, which is exactly same as the value, optimal value of the primal problem. And we know by using strong duality theorem that the feasible solutions of the primal and dual problem which are giving same optimal value or same objective function value are actually the optimal solutions. So that means the optimal solution of my dual problem becomes 3 by 4, 1 by 2, 0, 0. So this is the optimal solution with z value as 21. So what we did, we had the information about only the primal variables. We were able to solve the primal problem graphically because it is a two variable problem. We found the optimal solution of this problem, and by using complementary slackness conditions, we found the optimal solution of the dual problem. And we see we really don't have to look for the B inverse here or the simplex table. This is a very handy. But in many practical problems, graphical method doesn't work because the number of variables are more than two. So if we are solving the problem by using simplex method, can we apply the complementary slackness conditions and obtain the optimal solution of the dual problem? Answer is yes. So in the next example, we will understand how we can apply the complementary slackness conditions on a simplex table. So let us discuss second example. Example 2. Consider the following linear programming problem. Maximize 4x1 plus 10x2 subject to the constraints 2x1 plus x2 less than or equal to 50, 2x1 plus 5x2 less than or equal to 100, 2x1 plus 3x2 less than or equal to 90, x1, x2. This is again a small problem with two variables only and can be solved by graphical method. But we will solve this problem by simplex method. So after solving the problem by simplex method, we have obtained the following table. So the optimal table of this problem is given as this. So my variables are x1, x2, s1, s2, s3. Here s1, s2, s3 are my slack variables. So my basic variables are x1, x2, s3. So these are the entries of my simplex table. S1 is 5 by 8 minus 1 by 4 minus 1 by 2. S2 is minus 1 by 8, 1 by 4 minus 1 by 2, 0, 0, 1, and the 150 by 8, 25 by 2, 15, and my zj minus ej rows gives the value 0, 0, 0, 2, 0 with the set value as with z value as 200. Now let us write the dual problem first. So my dual problem is minimize 50 by 1 plus 100 by 2 plus 90 by 3 subject to 2 by 1 plus 2 by 2 plus 2 by 3 greater than or equal to 4, y1 plus 5 by 2 plus 3 by 3 greater than or equal to 10, y1, y2, y3 are greater than or equal to 0. Again, to apply complementary slackness conditions, we must know the information about the slack surplus variables. But it is evident from this simplex table that simplex table itself gives us the information about the slack and surplus variable. So we see in the primal problem we have total 5 variables, right? And out of these 5 variables, these 3 are in the basis, right? And you see the positive variables are x1, x2, and s3. So what information does this give? This tells us that if x1 is positive, that means first slack or surplus variable in the dual problem is 0. That means this dual problem is satisfied as a equality. That's all. Similarly, because x2 second primal variable is taking positive value, which is 25 by 2, taking positive value in the basis, that means second surplus or slack, whatever, here it is a surplus variable, it will take zero value. So it means this is also satisfies as an equality constraint. And thirdly, we have third slack variable is in the basis with positive value. What information does this give? So it means that my y3 is 0, right? So what we are left with? So on solving, we get 2y1 plus 2y2 is 4 because y3 is 0, and this inequality is finished because we have the equality now. Similarly, y1 plus 5y2 is 10. On solving this system, we get y1 is equal to 0 and y2 is equal to 2. So the complete solution of the dual problem is my 0, 2, 0. These are my three. And what is the objective function value at this solution? So 50 into 0 plus 100 into 2 plus 90 into 0. So this value comes out to be equal to 200, which is exactly same as the objective function value obtained at this solution. So that declares that this solution 0 to 0 is an optimal solution of the primal problem, of the dual problem. So if we are solving the problem by using simplex method, simplex table itself gives us the whole information. It tells us which of the variables are in the basis with the positive value, and with this and the information from these positive variables, we get the information about the dual variables and we solve the. This was all about the complementary slackness conditions of a linear programming problem.